Is a polyglot developer working with anything from edge computing to data processing pipelines. No, outside of work, she's a organizer and frequent speaker at the Malmo Elixir meetup and spends a bit too much time, I don't think so, honestly, on the Elixir Slack. So, welcome, thanks to be here, and please.
All right, should we get started? Can you hear me? All right, everyone can hear me? Cool. So, got a few things to pick up. Maybe closer? Over here? Better? I don't know what's easier. Okay. First of all, if I am speaking too quickly, please do some kind of indication to get me to slow down a little bit. I have a tendency to do that. I'll do my best not to. If it looks like I am forgetting to breathe, do some kind of okay, remember to breathe, okay? That would be great, thank you. Okay, let me skip, I have an extra slide and then I have this slide as well. Okay, so who wants to hear me speak a little bit of Spanish? Like a tiny bit? Okay, all right. Okay. Let me see. Hola a todos y bienvenidos. Me da mucha emoción poder abrir este día de conferencias de Codebeam en México. Muchas gracias por la invitación. Estoy muy contenta de estar aquí. El día de hoy quiero hablarles sobre Distributed Elixir Made Easy. Okay, did it. Right. Next year, maybe I'll do the whole thing in Spanish. We'll see. Yes. I'll do my best. Okay. Welcome to everyone. I'm super excited to be here doing the opening keynote at Codebeam in Mexico. And on top of that, getting to speak about distributed Elixir, which is something that's really cool and really fun, right? And I'm super excited to talk about some ways you can make it kind of easy to bring that into your stack where, well, I'm going to get into that, the specifics. But first of all, let me introduce myself again. My name is Jonah Larson. I'm a staff software engineer at Duffel. I need to figure out where the little thing for the introduction came from because it's not really up to date. I live in London now, not Malmö, but I am from Sweden. Here you can also see my socials. This is very important. If you've seen me speak before, I like to make the joke that my sort of sense of self-worth comes from how many followers I have on Twitter. At least people think it's a joke. It's actually totally true. So please, go ahead and follow me on there. That'd be really cool. I also want to introduce you to my cats. This is Monkey and Blue. Yeah. Some applause for Monkey and Blue. They're actually they do a very important part in this presentation because I get a lot, I am a very anxious person under normal circumstances, and doing public speaking is a lot worse. It's a lot of pressure getting up on stage, but what's actually even harder is the weeks before the presentation. Once I'm up here, it's kind of okay, at least it's only going to be another 45 minutes and then I'm done. But I've spent 3 weeks, suffering with anxiety. And putting my cats in the presentation helps a little bit because, it's not a little bit less scary to work on. So coming to an Elixir conference in Mexico, probably the least thing you'd expect to hear is Swedish. But I'm going to say, I have a little phrase here, Kärt barn har många namn. Basically, in English, that's something like, beloved child has many names. And in other words, the more you love something, the more names you tend to give it. And I want to start by taking the opportunity to avoid a little bit of confusion or let's say complexity. When we talk about Elixir Erlang, we've got Erlang VM, we've got OTP, we've got all of these different words, right? This is an Elixir talk, so I'm just gonna call everything Elixir to avoid confusion, to avoid like bringing in all this terminology. And then you can just like assume that everything I'm talking about, you can do in any language on the Beam, right? All of it is built into the machine itself. You don't need to worry about it. It's available to anyone who's using the Beam. But I'm just gonna call it Elixir for now. On top of that, the topic is distributed Elixir. There are also other names for that. You've got like distro, you can talk about clustering and stuff. I'm gonna stick to just saying distributed Elixir. All right, does that make sense to everyone? Yeah. Cool, perfect. So this is my goal. I want you, hopefully, if I'm successful, to come away knowing some places and some ways where you can easily and safely use distributed Elixir to solve your problems. I think distributed anything is a hugely complex topic, and it's enormous, right? It's a million talks right in there. I'm not going to go into a lot of detail on everything that I'll be talking about, but because I have a lot to cover. But hopefully, I can inspire you a little bit to go read up on stuff, to go experiment with stuff. There are lots of resources online that you can use to read more. So more than anything, like my stretch goal on top of this is to inspire you a little bit to play around with this. So as a software engineer working on projects, I'm sure everyone's, very much on the same page that it's very important to define the scope of the project. I would say that from personal experience, it's pretty much just as important, or maybe even more important, to determine what's not in scope. So here you have that kind of laid out. I will be talking about, I'll give you a very high-level description of processes and message passing. I'm going to quickly describe what I mean by distributed Elixir. I'm going to talk about risks, and I'm going to talk about benefits, how to get started, tips and tricks, some examples of good use cases, and also like a little bit of a mention of existing libraries that use distributed Elixir. What I will not talk about, I will not talk about complex distributed systems. That's kind of the opposite of this talk. I want to talk about like stupid, simple distributed stuff. I'm not going to be talking about the underlying protocols, partly because, or mostly because I don't know them. As a user of a system, you don't necessarily need to know how it's implemented under the hood. You just need to know how it works, right? And I am way too scared to dive into the source code of the Beam. Like, that's terrifying, right? I'm not going to talk about large clusters. There's a little bit of a mention at one point, but the solutions for how to run a lot of servers together, all connected, I would recommend that you look up one of the many talks made by people from WhatsApp talking about how to run large clusters. I'm not going to talk about consensus algorithms because I don't have a PhD. And as mentioned, I'm not going to talk about Erlang or other Beam languages, but remember that everything this is built on is part of the Beam itself. It's part of the virtual machine, or part of the tooling that comes with it. So don't worry, everything, like, you have access to all of it anyway. I'm also not going to talk about how to replace your entire stack with just Elixir, because again, you're bringing in a lot of complexity, and the point of this is to, like, let's find some parts that are quite easy to implement and easy to use. So let's kick it off with a short explanation of message passing. Again, this will not be exhaustive. I'm going to skip over a lot of stuff. And if you want to read more about it, then there's tons of resources online. And hopefully you will if there's stuff that comes up that you're not really sure how it works. So first of all, processes. These are the workers of Elixir. Everything that happens, all your code, everything that's running on the machine happens in the context of a process. Every process can only do one thing at a time. If you want concurrency, if you want multiple things happening at the same time, you need your processes to communicate. Now, in Elixir, isn't he adorable? I love that picture, it's so cute. This was when he was small, and like, he's bigger now, but he still does this. He has like the furs like hanging over the side and stuff, but he still gets in that box. Yeah, so the most basic way of sending a message from one process to another process in Elixir is send. It's pretty simple. It requires a destination and a message. It's pretty much like putting a cat in a box, handing it over to someone else, they open that box, and they get a cat. And you can see why people are very interested in this technology. It's some really cool technology. Now, of course, the process that's receiving the message has to do something as well, which you do with receive. That's how you specify, how do I handle getting this message, right? Now, most likely, if someone sends you a cat, you're going to be overwhelmed with gratitude and be very happy, and you want to send back a thank you note, right? So using send and receive, you can set this up two ways, right? Or both ways. So you send a message, that message is received by process B handles that by sending a message back to process A. You set up this sort of the logistics of message passing back and forth. Now, on top of where send is kind of a low-level tool for this, on top of that, you have GenServer, cast, and call. There are a few other things as well. But basically, at some point far in the past, the ancient wizards of Erlang collected, all their collective wisdom. They pooled it all, and they came up with all of these best practices for how to communicate between processes. And that's where GenServer, cast, and call come in. And basically, it still works the same way. You just need a destination and a message, and that's pretty much it. With GenServer.call, you have the sending a message and getting a response back kind of covered by the function itself. And then you've got the other side of it, where the receiving process defines callbacks to handle these messages and decide what to do with the messages, right? So obviously, you can tell that I'm skipping over a lot, right? This is just to get us to the point where we can talk about the next step. But again, if you want to read more about this, tons of resources online. So here we are at distributed Elixir. And so this is where we want to send a message or talk to another process that's on a different machine or a different instance running Elixir. And it works the same way. The same functions that we talked about passing messages between processes on a single machine, we use the same functions to communicate between processes on different machines. You still just need a destination and a message. And that is something that's really, really, really cool. I really want to emphasize this. It behaves the same way, right? I think this is something that's kind of unique for Elixir, and Erlang and all the other languages, in that where you might have experience from other languages. You might have experience setting up multiple servers that communicate with each other. You might have microservices. But then you probably implemented a JSON API or a GraphQL API, or you used gRPC or something to communicate between these servers. And a gRPC function doesn't behave the same way that a local function does. And what's so cool about Elixir is that you can set up functions that work exactly the same way, and they don't even know if the process they're talking to is on another server, because it doesn't matter. So, as mentioned, skipping over a lot, I could go into talking about all the specifics of how to set up gen servers, how to manage them, talk about supervisors, all of that stuff. I'm not going to. We have enough now to move on. So, first of all, high-level benefits. When I introduced distributed Elixir at work, I started out by kind of asking around in the community to try to gather information on what do people see as the benefits of using distributed Elixir. And I collected all of the answers that I got, and I realized that there were two main categories. People use distributed Elixir for performance and for reduction of complexity. So on the performance side, you have like a few things like you can sometimes build things with fewer network hops, and the fewer network hops, the happier your life is. Also, you've got like staying in the Elixir world means more efficient serialization of data. You don't need to switch between different formats, et cetera. That also comes up on the reduction of complexity side, where you only need one representation of your data. If you've ever used a JSON library to serialize a struct, you know why this is nice, to not have to worry about like, how do I put things in different formats? It also means that you can sometimes avoid adding more systems to your stack. You're sometimes able to build things inside of Elixir where you would otherwise need to bring in Redis or something else. But I think the big one is that it uses the same observability as the rest of your code. I think this is really cool. Like if you're bringing in, I don't know, Sidekick or Redis or RabbitMQ, you probably want to have some observability on that system to monitor how that system is performing. Then you have to figure out, how do I do that? While if you can use your Elixir code to build these things instead, you probably already have observability set up for your own code. You've got logging, tracing, you've got metrics, all of it is already there. So let's talk about why people might avoid using distributed Elixir. And your experiences may differ. These are some of the things that I've heard and seen. I think they're all healthy, reasonable arguments. I think a big one there is sort of we're used to solving problems with other techniques. And I think the lack of confidence with gen servers, which is totally fair. Like you can work as an Elixir engineer for many years and you're building a Phoenix MVC stack. You might not even define a gen server at any point. You don't really need to think about that. There are processes everywhere under the hood, right? But you don't necessarily need to think about it. So let's tackle those concerns head on. First of all, I realized I didn't mention this one, but network failures, I mean, whenever you introduce a network to anything, you're going to have a problem. That in itself is not specific to distributed Elixir. I think some libraries, the way they're designed, Ecto, for example, has a very convenient kind of, you do a database lookup, you get some data back, or you get nil back. It kind of hides the fact that there's also failure, which you realize when your database goes down and your server explodes with exceptions everywhere. But with distributed Elixir, you also have to worry about something else. So imagine that you have these 4 servers set up. They're all talking to each other. They're all connected. Then the bad thing happens, and you have a net split. And now 2 of the servers are aware of each other, and the other 2 are aware of each other. And they might all be accessible from the outside, but they're not communicating with each other. And like that adds, that's an additional risk to your system. Again, anything that's distributed is complex. The more stateful functionality that you put into memory on your machines, the more you rely on your machines to talk to each other, to coordinate, to communicate, the more you have to worry about deployments, crashes, net splits, all of it. Again, the big one, I think, is lack of confidence. As mentioned, you can work with Elixir for many, many years and never really touch this stuff, which is fine. Like, there's nothing wrong with that. And it really, Phoenix is a really cool library. You can build really nice things with it. And you might, again, be used to solving problems a different way, from a different language, from a different platform. But looking at distributed Elixir, it's another tool in your tool belt. It's something that you might want to use for specific things. As mentioned, there might be some scaling issues if you're running very large clusters. I think in the community, you often hear 40 servers as kind of a limit. There are definitely ways around this. It may have been improved recently. It can be solved, but it takes some expertise. So we talked about risks, we confronted the risks. Now let's talk about how to mitigate the risks. So this is, and you probably want to take pictures of this because this is really cool. This is a non-exhaustive, easy distribution checklist. The name is a bit of a mouthful. I'm working on it. But actually, we have this in an internal document, which is kind of a like, don't do distributed Elixir unless you feel like completely comfortable with all of this stuff, right? So basically, you have to assume that you might lose some data at some point. You have to assume that it's okay if some data is lost or wrong, or if you can't access it. If you can't tick these boxes off, you might be better off putting your things in Postgres or something that gives you these guarantees. You can technically build things still, but it might be complicated. And then you should be even more excited about this because this is totally original new content. This is the flowchart version of the same thing because everyone loves flowcharts. Okay. Now, follow these rules, and you'll be able to sleep as peacefully as this little dummy cat. So now that we talked about risks and stuff, I want to talk about some useful techniques that kind of follow this pattern of it's okay if some data is lost, and I don't want to add too much complexity into my stack. So first of all, to play around with distributed Elixir, you can easily do that locally on your machine. Start up 2 terminals, run the 2 commands. You see at first we call node.list. There are no nodes connected. Then next step on server A, I call node.ping, give it the name of server B. The reason you want to use node.ping instead of node.connect is because it responds with Pong, and that's really funny. If it fails, it responds with Pang. Node.connect has no funny answers. After the ping, you can see that now calling node.list, there's another server connected. This is amazing. The 2 servers will now, or 2 machines will now, instances, will now have a heartbeat set up. They'll communicate. If one of them is closed down, the other one will pretty much immediately realize that the other one is down. But doing that, manually logging into your servers and calling node.ping isn't very scalable, even though it's fun. So you probably want to use a library like libcluster. Libcluster is super simple under the hood because it's just using the underlying platform. So I definitely recommend looking at the code. It's pretty straightforward to understand. It allows defining strategies for discovering nodes, right? So this example here uses a Kubernetes DNS strategy where you create a headless service, and it's basically a DNS record that you can hit the DNS record and you get a list of IPs, and libcluster will automatically connect to all of those IPs, which means that, let's say you're running in Kubernetes, you've got auto-scaling, you've got deployments, servers going up and down, it will just figure it out for you. Static clusters are a lot easier to work with, but most of what I'll be talking about is really about dynamic clusters. Okay, so now that you have your cluster set up, now your servers are connected, you're going to need to be able to monitor them. This is a very simple skeleton that you can use to set this up. It's a process. The thing that you really want to pay attention to is the net kernel monitor nodes true. This tells the machine that you want to, subscribe to updates. And whenever there's an update, one of these handle info callbacks will be called, whether node up or node down, which means you can do whatever you need there, right? You can put in some logging, you can put in metrics, you can react to this whatever way you want. Next, a really quick interlude, consistent hashing. This is something that's really cool and really useful when building distributed stuff. But I find Wikipedia computer science articles impossible to read. They're so dry. So instead, we're going to learn through example. There is a Discord library called xhashring where we follow this example. So we start by adding nodes, A, B, C. Let's just say these are our servers, our server names. We then call find node and give it a key. It will give us back the node that's responsible for that key. If we remove the node, the next example, find node some key, will return A because B is not there anymore. But if we put B back in, we get B again. And this is really cool, right? We can kind of rely on this to give us consistent answers. And even if we remove C, it's still B. It's still responding B. And this is true most of the time. That's the point of this, is most of the time you'll get reliable results out of it. And why you would want to reliably be able to associate a key with a specific node, if you've ever worked with Kubernetes or other orchestration tools and you've had these servers going up and down, you probably realize why. So let's extend the monitor example. If the code is getting too small, there are a few seats in the front if you want to come sit in the front. So it's the same example as before, but this time we add nodes to the ring. Whenever there's a new node that shows up, we add the node to the ring. Whenever a node goes away, we remove it from the ring. That way the ring is now, we can keep the updated state of all of our nodes in that ring. So let's look at a very simple cache example. I mean, this is pretty much as simple cache as possible. It runs locally on one machine. It's registered with a name, so you can easily find it. You can get a key from it, or you can put a key on it, and it keeps that map going, right? Now extending this from only running on one machine, only being accessible on one machine, to giving consistent results across a cluster, only requires adding that single line to get and a single line to put. That's all you need to do to take this local cache and make it cluster-wide. So by using the distribution node, you can find the node, the distribution ring. You can find which node is responsible for each key. So you have your cache key, you will know which node has that cache key. And that's pretty cool. And this handles auto-scaling just fine without too much of an impact on the hit rate. But what about deploys? Well, so when I was drawing this, I was drawing all the arrows, and I got so distracted by the cool pattern it was forming that I forgot to rename some of the nodes, so they're not very consistently named. But basically, we do rolling deploys and dynamic clusters. We have lots of servers showing up, and then a lot of servers being shut down. And we want to keep that cache state across the deployments. And we discussed different ways of solving it, and we decided to go with the stupidest one possible, which is whenever a new server starts up, it asks all the existing servers for all their data. Because that way, you know that the right data is on your server, because every server now has a full set of the data. Obviously, this comes with risks. The handovers become quite heavy because you need to get all of the data. But it's a pretty good starting point, I think, for how to maintain state across deployments without adding complexity. Because implementation is like this, right? You need to implement a handle call handover that just hands over all the data you have. And then while you're starting up a Gen server using handle continue here, because it takes a while, you do a multi-call, which is a broadcast call across the cluster. You get all of your results back. You just smash them together into a single map, and then you're done. Now you have the whole set of data on your process. So this is just, I think, you should treat this as a starting point. This is not optimized. This is not pretty. It's not elegant. But it's a good starting point with like minimal implementation requirements, and it works pretty well, really. Sorry, is this accurate? 7 minutes left? Really? Wow, okay. So there is a little caveat to using genserver.call. When you're doing it across the network, you might see more frequently timeouts. You might have more errors where a server is going down as you're talking to it, et cetera. During a deployment, you probably, the default behavior for genserver.call is to exit, crashing the caller. If you know what you're doing and you're sure that you want to do this, you can use this simple snippet to to convert the exits into error tuples instead, and then you can handle the error states. This is again very useful when you don't care if you lose some data, if you're not able to access some data, you can just handle it. I'm gonna skip that one. So, of course, as professional software engineers, we all love writing tests, right? It's the most fun part of our job. And luckily for all of us, there's a convenient way to write tests with distributed Elixir. It's called local cluster. Again, this is another library that I would recommend that you just go look at the source code, because it's like this much. It's tiny because it all comes with the platform. This is just a little wrapper on top of it. But it's basically a convenient way to start nodes inside of a test, and it will start another machine sort of on the side. One thing to be aware of, though, is that if it takes a long time for your machine to start up, this will also take a long time because it's starting up a whole instance of your app. Now, if you the first thing you probably ever you like the. Your first experience with distributed Elixir might be global. This is a convenient way to, instead of registering a name locally on your machine, you register it globally across your cluster. The sort of runtime itself will kind of maintain that there's only one instance running at any point, and you can, from any server, just use the tuple and global in the tuple in the destination to specify that you want the globally named process, and Elixir will just find it for you and ensure that everything works just well. This is a water break. It really looks like he's doing a podcast or something, right? Yeah. So, to continue with the sort of inspiring you, I'm going to give you some examples of safe, high payoff, practical use cases. So one is rate limiting. It kind of depends on your use case a little bit, but at Duffel, way back, we used to have use a rate limiting library that ran in memory on the machine. It was just an ETS table, basically. And we had 3 servers running, and each server would have a different counter on each IP, so it depended on which one you hit, and you got different quotas. So we used this trick with distributed with the hash ring to ensure that each IP, which was the key, went to the node that was responsible for it. And so by just adding a few lines, we could take this machine or instance local rate limiting library and make it global over the entire cluster. And that works really well for us because we have short rate limits, seconds, minutes. And so if we lose some data during a deploy, which we do because we don't do handovers, it's okay. It doesn't really matter that much. Someone gets to do a few extra requests, it's fine. This is a very good example of a low effort, high reward. Another way you might solve rate limiting is you would bring in Redis, and then you're bringing in all this extra stuff that you have to worry about. And you might be paying more money as well. Caching, we already talked about this. We can very easily create a distributed cache. Kind of extending the cache example, something we found was that we had certain cases where, isn't that a really silly picture? We had some of these errors that kept happening, and we would put them in Sentry. It wasn't even with a stack trace or anything, and we just get this enormous ticket that just kept building up with events, and everyone's ignoring it. We replaced that by creating kind of a cache that we would fill, and it would keep track of how many times it saw this error or this error. And we have an internal dashboard, which is also Elixir, and so we could very easily just do a cross-cluster call to pick up all of the aggregated reporting and show a report on the web page. And we didn't need to build anything extra. There's no database, there's nothing to do very simple reporting. So I also want to talk quickly about some example libraries using distributed Elixir in the wild. I think the big one is Phoenix PubSub. The default adapter is actually PG2, which is really funny. PG2 is not the new version, that's Process Groups 2. The new version of Process Groups is actually PG, not PG2, because from what I understand, there was an experimental version called PG, and then it was like they made a proper version, so they called that PG2, and then someone wanted to fix the PG2, and instead of calling it PG3, they called it PG1, because that was never technically taken. If you want to experiment with a little bit more complexity, you can look at the library Horde, made by Derek Cron, who's a really cool guy and really nice, by the way. And this allows you to create like cluster-wide supervisors where you can start up processes and you don't really care where they're running. And this library will kind of maintain that it's running somewhere, but it doesn't matter where it's running. So this one says I'm done, but this one says I'm only at 35 minutes. I'll keep going a little bit. Cool. So I have a bonus slide. This is the mystery of the swoosh crash. So I don't know if anyone's read, I can't remember what company wrote an article, but someone wrote an article about this. We also found the same issue. I never got around to writing the article, so I got scooped on that, whatever. But we can still talk about it because it's a really cool example of weird things that can happen when you do distributed Elixir. So we had recently had an increase in volume on our production servers, and so we were running more servers than ever, right? We're running a lot of servers. And then we slowly started noticing this weird thing where during a deployment, sometimes it would just go through just fine. Sometimes we'd have like one server crash and then get restarted and everything was fine. Sometimes it would be 2, 3. Sometimes we'd have 10 servers crash in a cascade. They would eventually get restarted and everything was fine. There was like minimal impact on production, but something was clearly wrong here, right? And so I went diving into our logs, and the only error message I could find was this. It's the only error message. There was nothing else. Kernel PID terminated, application controller, application terminated, swoosh shutdown. So what is swoosh, and why is swoosh shutting down? And swoosh is an email library. It's a library for sending email. Why is this crashing our servers, right? And I remembered seeing something about a swoosh process running globally and being shut down locally on my machine when I was experimenting with running clusters locally. And I dug into the source code of swoosh and I found this. So can anyone see where the crash is? Like what is causing the crash? It's totally fine if you can't, because it took me forever to figure this out. It would be embarrassing for me if you just figured it out immediately. This piece of code is pretty smart, right? So you have this, it's an internal process that runs inside swoosh. It tries to start globally, register itself globally. If someone else has already registered this name globally, it fails with already started. And in that case, it links to that globally started process. So what this means is, if that globally started process ever shuts down, the link will ensure that this process also crashes, and then the supervisor will restart that process, and it will try to register the name globally, right? And then if you combine that with lots of servers starting and shutting down at the same time, and you look at a little piece of documentation under supervisors, it says max restarts, the maximum number of restarts allowed in a time frame, 3. Max seconds, the time frame in which max restarts applies, defaults to 5. So if you have more than 3 crashes in 5 seconds, what does the supervisor do? It crashes. And what is the supervisor of this process in the swoosh library? Well, it's the swoosh application. So what was happening was we had a lot of servers running, and then we started up a bunch of new servers, and then we started shutting down the old ones. And one of them had the globally registered process, right? So it shut down, sending a message across all the servers telling them all to shut down. So all of them would shut down, and all of them would then start up again, racing to register this name globally, right? But what if one of the servers that's shutting down is the one that wins the race? It will, half a second later, also shut down, killing the process again, telling everyone to shut down again. And all it took was this happening 3 times in a row, and all of the supervisors on the servers with this happen 3 times in a row would crash. And the supervisor is the swoosh application, so the swoosh application crashes, which crashes the whole server. That's where our shutdowns came from. The fix was pretty simple. This process was like a local mode process that was meant for like local development. So all you had to do was set local mode false. But unfortunately, it's true by default. So it's pretty cool that someone else found the same thing. But yeah. Now, you all probably feel a little bit like this. It's been a lot. I've gone through a lot of things. You're still paying attention, but you might feel like a little bit tired and overwhelmed. I am too. So let's finish it up. To do a quick recap, what we talked about we talked about message passing, we talked about what distributed Elixir is. We talked about risks and benefits, talked about how to get started, some examples of good use cases, and some examples of libraries that use this. And again, my goal was that you should come away from this talk knowing, or at least having an idea, of where you can safely and easily use distributed Elixir to solve your problems. And the stretch goal was to inspire you a little bit to play around with this stuff. And hopefully I did.
Thank you. Thank you again for the great talk. So we're going to pass to questions. Any questions? Please don't be shy. Okay, let me. Francesco.
Hi, Joanna. Thank you for your great talk. It's not a question, but more a comment, which kind of has been lingering in my mind. And you said, it's the adoption of distributed Elixir is not common, and that there's a fear for it. Whilst, if you look at the Erlang community, it's probably day 3 of the course, and everyone starts using it. And the reason, I think, and you were spot on with it, is that we tend to use bare bones Erlang. We don't use libraries, we don't use dependencies. We just use processes, and you've got 2 processes, they don't share memory. So if those 2 processes are on the same node or on separate nodes, it just doesn't matter. Yeah. And I think, you were right on where, hiding this complexity of distribution in libraries is a solution for the Elixir community. So you were spot on when describing these libraries. So thank you very much. Yeah.
Thank you.
We have another. Okay, let's go here. Please.
Hi, you mentioned about some good cases for using distributed Elixir, but which one or which will be the bad cases? Because, well, we know that maybe sometimes an Elixir or Erlang application in one node is enough, maybe, in some cases. But in your experience, which will be bad cases about distribution?
Yeah, I would say, it's not a question of whether you can do it or not, right? You could build anything. But where you're probably going to make your life difficult is if, say, you're building a banking system and you want to make sure all the accounts are exactly correct. And you're distributing that with like a process that represents the account, and you have like these messages going over the cluster. And then you really have to worry about things like net splits. You really have to worry about servers being unavailable for certain periods of time, et cetera. And you have to write all this code to handle those cases, which is totally doable, but you're adding a lot of complexity. I think anything like if you're taking payments, like any kind of thing like that is where you would probably want to be careful. I'm not saying not do it, I'm saying, it takes more effort.
Thank you.
Okay, give me a minute. Just, please.
Thank you for your talk. I think you maybe know this library called Swarm that is built on top of libcluster. If so, have you experimented with it, and what are your thoughts about it?
I have not experimented with it. From my understanding, it works similarly to Horde. So it has these concepts, right, of running processes across the cluster and putting them on different servers, etc. Yeah, that's my understanding anyway.
Okay. Thank you.
Let's go here. Thank you for your great talk. My question is, have you ever tried to set up a pool of Gen servers among different instances? Do you think that is a good idea? Or maybe relate on another technology for load balancing?
Okay, sure. I have not, but it is something we've experimented with the thought of doing it. We have a certain workload that I talked about at a different conference, where we use GCP PubSub as a message queue. And we discussed, instead of having the message queue and then workers that pull messages off the queue, we talked about using, say, process groups to define workers across the cluster, worker processes, and then having some algorithm like modulo or round robin to distribute work across them. I think that's totally doable. It's a good use case. It's a fun use case, at least.
Thank you. More questions? Oh, okay. Well, thanks again. One question here? No? Okay. So, thanks again, Joanna. Great talk. So,